For aircraft operating under instrument flight rules, an instrument approach or instrument approach procedure is a series of predetermined maneuvers for the orderly transfer of an aircraft under instrument meteorological conditions from the beginning of the initial approach to a landing, or to a point from which a landing may be made visually. The concept was also commonly known as a blind landing or blind approach when first introduced, although these terms are no longer common. There are two main classifications for IAPs, precision and non-precision. Precision approaches utilize both lateral and vertical information. Non-precision approaches consist of localizer only, circle to land, VOR, and all GPS approaches. Publications depicting instrument approach procedures are called terminal procedures, but are commonly referred to by pilots as approach plates. These documents depict the specific procedure to be followed by a pilot for a particular type of approach to an airport. They depict prescribed altitudes and courses to be flown, as well as obstacles, terrain, and potentially conflicting airspace. They list missed approach procedures and commonly used radio frequencies. Before satellite navigation was available for civilian aviation, the requirement for large land-based navigation aid facilities generally limited the use of instrument approaches to land-based runways. GNSS technology allows, at least theoretically, to create instrument approaches to any point on the Earth's surface. Consequently, there are nowadays examples of water aerodromes that have both land-navigation-based as well as GNSS-based approaches. Basic principles: instrument approaches are generally designed such that a pilot of an aircraft in IMC, by the means of radio, GPS, INS navigation, or ground-based radar can navigate to the airport, hold in the vicinity of the airport if required, then fly to a position from which he or she can either obtain sufficient visual reference of the runway to make a safe landing, or execute a missed approach if the visibility is below the minimums required to execute a safe landing. An instrument approach procedure may contain up to 5 separate segments. These segments are: arrival segment, the segment from where the aircraft leaves an en route airway to the initial approach fix. Initial approach, the segment from the initial approach fix to either the intermediate fix or the point where the aircraft is established on the intermediate or final approach course. Intermediate approach, the segment from the IF4 point, to the final approach fix. Final approach, the segment from the FAF or point, to the runway, airport, or missed approach point. Missed approach, the segment from the MAP to the missed approach fix at the prescribed altitude. When an aircraft is under radar control, air traffic control may replace some or all of these phases of the approach with radar vectors to allow traffic levels to be increased over that which is possible when following the full procedures. It is very common for ATC to vector aircraft to intercept the final approach nav's course, for example, the ILS, which is then used for the final approach. In case of the rarely used ground-controlled approach, the instrumentation is on the ground and monitored by a controller, who then relays precise instructions for adjustment of heading and altitude to the pilot and the approaching aircraft. Non-precision approaches and systems, VHF omnidirectional range, tactical air navigation, non-directional beacon, a Euro ground-based transmitter for aircraft equipped with an automatic direction finder. Simplified directional facility, satellite navigation systems, such as the American Global Positioning System. LNAV and LNAV-VNAV approaches require receiver autonomous integrity monitoring which detects problems with GPS satellites. LPV and LP do not require RAIM since they utilize SBAS correcting signal like Wide Area Augmentation System or European Geostationary Navigation Overlay Service. Required navigation performance, a system that utilizes onboard performance monitoring through the aircraft's flight management system, localizer, localizer-type directional aid, surveillance radar approach, a Euro, airport surveillance radar, a Euro military designation for SRA. Precision approaches and systems, ground-controlled approach, mostly military, GNSS landing system, instrument landing system, Joint Precision Approach and Landing System, Microwave Landing System, Precision Approach Radar, Military, Transponder Landing System. Low visibility approaches, Most instrument approaches allow for landing in conditions of low visibility. See Airport Requirements section. There are air traffic control considerations with low visibility approaches. There must be longer gaps between aircraft on final approach both to protect the ILS signal and to cope with slower runway vacating times. Concepts in detail. Decision height or altitude equals. A decision height or decision altitude is a specified lowest height or altitude in the approach descent at which, if the required visual reference to continue the approach is not visible to the pilot must initiate a missed approach. The specific values for DH and/or DAR at a given airport are established with intention to allow a pilot sufficient time to safely reconfigure an aircraft to climb and execute the missed approach procedures while avoiding terrain and obstacles. A DH-DAR denotes the altitude in which a missed approach procedure must be started. It does not preclude the aircraft from dipping below the prescribed DH-DAR. A decision height is measured AGL while a decision altitude is measured above MSL. Minimum descent altitude equals. The minimum descent altitude is the lowest altitude to which descent is authorized on final approach, or during circle-to-land maneuvering in execution of a non-precision approach. Unlike with DH or DAR, a missed approach need not be initiated immediately upon reaching the altitude. A pilot flying a non-precision approach may descend to the MDA and maintain it until reaching the missed approach point, then initiate a missed approach if the required visual reference was not obtained. An aircraft must not descend below the MDA until visual reference is obtained, and which the aircraft can land while performing normal maneuvers, which differs slightly from a DH-DAR in that while the missed approach procedure must be initiated at or prior to the DH-DAR, because of its vertical momentum, during a precision approach an aircraft may end up descending slightly below the DH-DAR during the course of the missed approach. If a runway has both precision and non-precision approaches defined, the MDA of the non-precision approach is almost always greater than the DH-DAR of the precision approach. Because of the lack of vertical guidance on the non-precision approach, the actual difference depends on the accuracy of the navaid upon which the approach is based, with ADF approaches and SRAs tending to have the highest MDAs. Direct approach equals. A direct instrument approach requires no procedure turn or any other course reversal procedures for alignment, as the arrival direction and the final approach course are not too different from each other. The direct approach can be finished with a straight-in landing or circle-to-land procedure. Course reversal procedure equals. When conducting any type of approach, if the aircraft is not lined up for a straight-in approach, then a course reversal might be necessary. The idea of a course reversal is to allow sufficiently large changes in the course flown, without taking too much space horizontally and while remaining within the confines of protected airspace. This is accomplished in one of three ways: a procedure turn, a holding pattern, or a teardrop course reversal. Procedure turn, a standardized way of reversing course to get lined up for final approach. The approach chart must indicate that a procedure turn is authorized for the approach, via a procedure turn barb symbol or a similar notation. Note that when a procedure turn exists for an approach, the maximum speed of the aircraft in the procedure turn is limited by regulations. The procedure turn is typically entered by tracking a navaid course outbound, and then turning 45 degrees off of the course. After that, the pilot flies this leg for a certain time, then conducts a 180-degree turn to get on a 45-degree intercepting course, and then re-intercepts the inbound course. Holding pattern, commonly referred to as the racetrack pattern. It is another method of course reversal, but it can also be used for losing altitude within protected airspace. A holding pattern used for this purpose is depicted in U.S. government publications as the hold and U of PT holding pattern symbol. The procedure has two parallel legs, with 180-degree turns between them. Teardrop procedure turn. If the controlled airspace is extremely limited, a teardrop may be used to reverse the direction of the aircraft and permit the aircraft to lose altitude. This procedure is shaped like a teardrop, hence the name. It typically consists of the outbound course flown at 30-degree angle to the reciprocal of the inbound course, and then making a 210-degree turn to intercept the inbound course. Back course approach equals. A back course approach is a type of approach in which a pilot flies the localizer's course guidance on the opposite side from the original direction it was primarily designed to be flown. A front course approach is usually depicted by the right half of the localizer symbol being shaded on the approach plate. A back course approach is depicted by the left half of symbol being shaded, as well as by clear indication that the approach uses localizer for the non-standard use. When flying a back course, the course deviation indicator needle deflects to the opposite side with certain types of equipment. This reverse sensing means that the CDI in the aircraft indicates the opposite of what the pilot is expecting on a standard localizer approach. That is, the CDI indicates to fly left when the aircraft in fact needs to fly right to intercept the approach course, and vice versa. Using CDI, if the needle moves away from center, the aircraft should be flown from the needle toward the center in order to re-intercept the correct inbound track. Reverse sensing does not occur on a horizontal situation indicator, which gives correct course guidance during both front course and back course approaches. The unshielded localizer transmits in both directions to give course guidance. Because the glide slope is not transmitted on the backside of the localizer, a back course approach is classified as a non-precision approach as it has no vertical guidance. The glide slope indications during a back course approach must always be ignored. This type of approach typically is found at smaller airports that do not have ILS approaches on both ends of the runway, where often the older localizer antennas are less directional. These transmit a signal from the back that is sufficient to be used in a back course approach. Newer localizer antennas are highly directional, and often cannot be used for a back course approach. Simultaneous close parallel approaches at some airports, multiple parallel runways are available for operations, but are so closely spaced that they present a hazard for simultaneous use under ordinary conditions. Simultaneous operations on such runways can be carried out using ILS and special precision runway monitor radars and 3 controllers, with special procedures known as simultaneous close parallel approaches. In this type of approach, 2 aircraft approach and land simultaneously on closely spaced parallel runways, with extra air traffic controllers assigned to monitor each approach path on special PRM radar. A zone between the runways is designated as the no transgression zone, and if either of the aircraft nears or strays into this zone, the other approaching aircraft is told to break off by the PRM controller, at which point that aircraft must veer away from the approach path. The aircraft must have 2 radios, one tuned to the tower controller in the usual way, and another tuned to the PRM controller. If runways are less than 3,000 feet apart but at least 750 feet apart, simultaneous offset instrument approaches may be used. The procedure is similar to that described above, except that one aircraft flies the ILS PRM approach, and the other flies an offset LDA PRM approach at an angle to the runway centerline. The aircraft flying the LDA PRM approach with glide path is positioned to be behind the ILS PRM aircraft, and must have the ILS PRM aircraft in sight before beginning a visual segment to the approach at or before the missed approach point. During the visual segment, the LDA PRM aircraft must keep the ILS PRM aircraft in sight as it aligns with the centerline of the runway. Visual approach A visual approach is an ATC authorization for an aircraft on an IFR flight plan to proceed visually to the airport of intended landing. It is not an instrument approach procedure. A visual approach may be requested by the pilot or offered by ATC. Visual approaches are possible when weather conditions permit continuous visual contact with the destination airport. They are issued in such weather conditions in order to expedite handling of IFR traffic. A pilot may accept a visual approach clearance as soon as the pilot has the destination airport in sight. According to ICAO Doc 4444, it is enough for a pilot to see the terrain to accept a visual approach. The point is that if a pilot is familiar with the terrain in the vicinity of the airfield, he/she may easily find the way to the airport having the surface in sight. ATC must ensure that weather conditions at the airport are above certain minima before issuing the clearance. According to ICAO Doc 4444, It is enough if the pilot reports that in his/her opinion the weather conditions allow a visual approach to be made. In general, the ATC gives the information about the weather, but it's the pilot who makes a decision if the weather is suitable for landing. Once the pilot has accepted the clearance, he/she assumes responsibility for separation and wake turbulence avoidance and may navigate as necessary to complete the approach visually. According to ICAO Doc 4444, ATC continues to provide separation between the aircraft making a visual approach and other arriving and departing aircraft. The pilot may get responsible for the separation with preceding aircraft in case he/she is the preceding aircraft in sight and is instructed so by ATC. In the United States, it is required that an aircraft have the airport, the runway, or the preceding aircraft in sight. It is not enough to have the terrain in sight. When a pilot accepts a visual approach, the pilot accepts responsibility for establishing a safe landing interval behind the preceding aircraft, as well as responsibility for wake turbulence avoidance, and to remain clear of clouds. Charted visual approach equals a visual approach that has a specified route the aircraft is to follow to the airport. Contact approach equals a contact approach that may be asked for by the pilot in which the pilot has 1 mile flight visibility and is clear of clouds and is expected to be able to maintain those conditions all the way to the airport. Circle to land maneuver equals a circle to land maneuver is an alternative to a straight-in landing. It is a maneuver used when a runway is not aligned within 30 degrees of the final approach course of the instrument approach procedure, or the final approach requires 400 feet of descent per nautical mile, and therefore requires some visual maneuvering of the aircraft in the vicinity of the airport after the instrument portion of the approach is completed to align the aircraft with the runway for landing. It is very common for a circle-to-land maneuver to be executed during a straight-in approach to a different runway, for example, an ILS approach to one runway, followed by a low-altitude pattern flying, ending in a landing on another runway. This way, approach procedures to one runway can be used to land on any runway at the airport, as the other runways might lack instrument procedures or their approaches cannot be used for other reasons. Circling to land is considered more difficult and less safe than a straight-in landing, especially under instrument meteorological conditions because the aircraft is at a low altitude and must remain within a short distance from the airport in order to be assured of obstacle clearance. The pilot must maintain visual contact with the airport at all times. Loss of visual contact requires execution of a missed approach procedure. Pilots should be aware that there are significant differences in obstacle clearance criteria between procedures designed in accordance with ICAO PANS OPS and US TUPS. This is especially true in respect of circling approaches where the assumed radius of turn and minimum obstacle clearance are markedly different. Rate of descent formula equals a useful formula pilots use to calculate descent rates. Rate of descent equals ground speed to 10, or rate of descent equals ground speed 5. For other glide slope angles, rate of descent equals glide slope angle ground speed 100/60, where rate of descent is in feet per minute, and ground speed is in knots. The latter replaces tan I plus or minus with I plus or minus /60, which has an error of about 5% up to 10 a degree. Example: 120 carats 5, or 120 carats/to 10 equals 600 fpm. The above simplified formulas are based on a trigonometric calculation. Rate of descent equals ground speed 101.27 tan I plus or minus, where I plus or minus is the descent or glide slope angle from the horizontal, 101.27 is the conversion factor from knots to feet per minute. Example: ground speed equals 250 carats, I plus or minus equals 4.5 a degree. 250 carats 101.27 fpm kt tan 4.5 a degree equals 1993 fpm. Airport requirements. Special considerations for low visibility operations include improved lighting for the approach area, runways, and taxiways, and the location of emergency equipment. There must be redundant electrical systems so that in the event of a power failure, the backup takes over operation of the required airport instrumentation. ILS critical areas must be free from other aircraft and vehicles to avoid multipathing. In the United States, the requirements and the standards for establishing instrument approaches at an airport are contained in the FAA Order 8260.3 United States Standard for Terminal Instrument Procedures. ICAO publishes requirements in the ICAO Doc 8168 Procedures for Air Navigation Services Aircraft Operations, Volume 2, Construction of Visual and Instrument Flight Procedures. Mountain airports such as Reno-Tahoe International Airport offer significantly different instrument approaches for aircraft landing on the same runway, but from opposite directions. Aircraft approaching from the north must make visual contact with the airport at a higher altitude than a flight approaching from the south, because of rapidly rising terrain south of the airport. This higher altitude allows a flight crew to clear the obstacle if a landing is not feasible. In general, each specific instrument approach specifies the minimum weather conditions that must be present in order for the landing to be made. References: Aeronautical Information Manual. FAA. March 7, 2013. Retrieved May 6, 2013. Pilot Controller Glossary. FAA. March 7, 2013. Retrieved May 6, 2013. Instrument Procedures Handbook. FAA. 2007. Retrieved May 6, 2013. Constant Angle Non-Precision Approach. Flight Safety Foundation. Augusta November 2000. Retrieved May 6, 2013. Electronic Code of Federal Regulations. Retrieved May 6, 2013. Precision Runway Monitor Training. FAA. March 19, 2013. Retrieved May 6, 2013. Audio and Multimedia Resources, Audio and Commentary of a Full Procedure RNAV Approach into Flint Bishop International Airport, Audio of a U.S. Instrument Rating Check Rider Euro Part 1, Audio of a U.S. Instrument Rating Check Rider Euro Part 2. External links, Aircraft Landing Systems Google Docs presentation.